So that's all I wanted to say about mutual information. And now we're going to take a bit of a left turn from the point of view of very classical information theory. But, this is a CS theory toolkit. So I want to now connect this to a topic in CS theory, namely the one we talked about in the last lecture, communication complexity. So there was like a great renaissance in like using like information theory to make big strides in communication complexity about 10 years ago. So I want to tell you about a little bit of that now. 10 to 15 years ago? 5 to 15 years ago? Okay. Okay, so today so far, I mean, if you think about communication, we sort of thought about implicitly like one-way communication when you have a probability distribution on input. So like when we were even defining entropy, when you're even defining entropy, we imagine that like maybe Alice gets a random variable X and she's now going to try to communicate its value to Bob using bits, and she's going to try to communicate it using as few bits as she can on average. And if you remember the last time when we were talking about communication complexity, we were talking about randomized communication complexity because it's kind of the interesting form of communication complexity. Well, quantum is interesting too, but we'll stick with randomized communication complexity. And the first model of randomized communication complexity, the one that we actually care about most, is where like its worst case model over inputs, what Alice and Bob are allowed to use randomization to like try to minimize the amount of bits they communicate. But we saw like the main way you try to prove lower bounds on that is by looking at distributional communication complexity. And anyway, distributional communication complexity is interesting in and of itself. So in distributional communication complexity, you have Alice and Bob, and they're trying to compute some function f, or do some task with their inputs f. And we do imagine that their inputs, x and y, are random from some distribution. So not necessarily independent, but we imagine that x and y get are random, possibly dependent inputs. And then once they have random inputs, you can actually, it's without loss of generality to only worry about Alice and Bob using deterministic protocols. So we're going to talk about, we talked about deterministic protocols in the context where you have random inputs. And this is like a little SAT analogy, not like the SAT like satisfiability problem, but like the tests in high school. It's like, we have like a colon here and like a colon here and like a double colon here. So in the simple one-way communication problem with distributions on the inputs, we talked about average communication cost, and we kind of related to this number, entropy. And we saw that, there's a sort of a one-way relationship, the average communication cost. Actually, I never mentioned this, but it has to be at least the entropy, and it's at most the entropy plus 1. And we sort of saw that they were in fact the same if you were allowed to like amortize. And so now you can ask for a similar sort of story where, instead of just one-way communication and like one input, you have communication complexity, like two-way back and forth communication. And they're sort of like the optimal cost for solving like a problem, or f, or computing a function f, under the assumption of like using, or the inputs coming from the distribution mu, and making error epsilon was some number. This was like the distributional communication complexity of f under distribution mu. And it turns out, the right information type construct number for two-way communication is this quantity called information complexity. So that's what I want to tell you about in the last 20 minutes. So let's first remember a little bit about this distributional communication complexity. So recall the setup. We have Alice and Bob, and they want to compute some function f of their mutual inputs, little x and little y. And they're going to use a communication protocol pi, which is, some system whereby they understand who will communicate which bits next and how they'll send communication bits based on their inputs, little x and little y. And pi does not necessarily have to always compute the function f. We're going to have error when we have randomized communication complexity. And we also imagine we have this mu, which is a joint distribution on inputs for both x and y. And we'll say that the error of protocol pi under distribution mu is just the probability that Alice and Bob come to the wrong answer. So this pi of xy is sort of the final answer they agree on. And it's supposed to be f of x and y, but it might not be. And the probability of these failing to be the same thing under mu is the error. And finally, the distributional communication complexity of function f under distribution mu with error rate epsilon, whoops, that was a mistake, is the least communication cost of a deterministic protocol pi that achieves error at most epsilon. Okay, so that's a recap from last time. So let's put that in a box. And now I'll tell you this thing, information complexity, which is ultimately going to be like a number associated with f and mu and epsilon. That's kind of like the information theoretic heart of this problem. Okay, so the information complexity of a protocol pi under a distribution mu is this. Okay, it's the sum of two terms that are kind of symmetrical looking. The first term is the mutual information of the random variable pi and the random variable y condition on x. So this is using that last most complicated definition, the conditional mutual information. So x and y are Bob and Alice's, well, Alice and Bob's inputs. And, you know, I'm kind of abusing notation a little bit here. Pi is, you know, a deterministic protocol. But here, what I really mean by it in this expression is I want to think of it as a random variable, but it doesn't take on numbers. It takes on like transcripts as its values. And so pi represents, imagine you like drew the inputs for Alice and Bob, x and y, little x and little y, and then you like gave them to Alice and Bob and let them talk according to this communication protocol pi. They would output like a stream of messages back and forth, and the whole transcript of what they output, not their inputs, but just the transcript of what they output, is the random variable pi. Okay, and so this quantity, conditional mutual information of pi and y condition on x, it has an intuitive meaning. And the intuitive meaning is the amount of information the conversation teaches Alice about Bob's input. So Alice, remember, knows x. Alice gets x. And so from her point of view, she sees this random variable pi, which is partly determined by x, and it's partly determined by y. And she sees pi, but she doesn't know Bob's input y. And so this mutual information, conditioned on what she knows, is kind of quantifying the sort of bits of information Alice learned about Bob's input at the end of the conversation. Okay, and similarly, the second term is the amount of information that Bob learned about Alice's input, sort of the amount of information in bits that Bob learned about Alice's input at the end of the conversation. Okay, and so the information complexity of pi under this distribution is the sum of these two information amounts. And I'll explain a little bit more intuition on that in a second, but let me just say now that it's a sort of an abusive notation too, but the information complexity of the problem or function f under distribution mu with error epsilon is sort of like imagine like Bob and Alice still want to solve the same task as before, but instead of trying to minimize the communication, the number of bits they send back and forth, they instead try to minimize this informational quantity. They try to minimize the sum of these two information amounts. So the protocol, which you look at the protocol which minimizes this amount of information, the amount of information that it creates among all protocols that achieve error at most epsilon is called the information complexity of f under distribution mu. And one thing I should have said before is like it's sort of the case, much in the same way that like well, I think I have it here on the next bit. This intuitive fact, much in the same way that like any successful protocol for transferring or transmitting, you know, a draw from x uses at least entropy of x bits. Similarly, any communication protocol which achieves error epsilon on distribution mu must send a number of bits in total, which is at least this information complexity. And the reason is like, you know, I mean, this is the number of bits that Alice learns about Bob's input from at the end of the conversation. And like, she already knows the whole transcript and she knows her own input x. So the only way she gets information about Bob's y is through like the bits that Bob sent to her. And the only way Bob gets information about Alice's input x is through the bits that Alice sent to Bob. So the total communication, which is the sum of these two things, bits Alice sent to Bob and bits Bob sent to Alice, intuitively has to be at least the information complexity of the protocol. And that's a not hard fact to prove. I should also mention a funny mathematical thing. You cannot formally write min here. You actually have to write infimum, if you remember that is, because it can definitely be the case that for a fixed problem or function f, and a fixed distribution mu, and a fixed error term epsilon, there's no one deterministic protocol that like solves the problem with error at most epsilon, but uses the least amount of, or conveys the least amount of information. It could be that like you have a series of protocols that all convey less and less and less and less information, because you're not putting any upper bound on how many actual bits of communication they have. So you could like imagine like Bob and Alice, who are extremely guarded and like they very slowly exchange some like actual bits of information that are bits of communication that are not too revealing about information. And so that's why at a math level, you have to take this infimum, the least lower bound, greatest lower bound. Okay. Right, so you can compare this, as I said, to this much simpler fact that if you want to, Alice wants to one-way communicate a draw from X to Bob, she needs to communicate at least entropy of X bits. And you might start thinking about the converse, like, is the reverse true? Like, can you always communicate not much more than this information complexity number of bits? Maybe if you allow amortization? Well, we'll get to that. So this information complexity, it's like a kind of a new concept. It was only really first defined in this paper from 2004 by Bar Yosef, Jairam Kumar, and Siva Kumar. And they proved in this paper one beautiful theorem about it, which is that it's perfectly additive. And this is like the analog of the fact that like the entropy of a bunch of independent random variables is the sum of the entropies of those random variables. So it's a more complicated fact. It says, okay, let's say you have some function f that you're trying to compute, and some target error epsilon, and some distribution mu. So that's like one problem. Now imagine that like, Alice and Bob were like, hey, you're going to have to solve f n times, and you're going to get n independent inputs, like, x1 and y1 will be drawn from mu, so they're not independent, but they are independent from x2, y2, and from xn, yn. So this mu to the, I don't know, O times n means make n draws from the joint distribution on inputs, x and y mu. And this f with like the superscript power n means they're trying to solve all these communication problems and figure out f of xi, yi, simultaneously with error at most epsilon for all the coordinates. So they get all the inputs, like Alice gets x1 through xn, Alice gets x1 through xn, Bob gets y1 through yn, and they have to figure out all the pairwise answers with error at most epsilon. You can again ask, like, how many bits of communication do they need, and how much information do they need? And it's a funny thing that, like, actually, you might think, like, well, they're independent instances. What can they do except, like, run the protocol, communication protocol n times? But they can do better than that. And it's similar to what we saw with communication, right? I mean, if you have to transmit one trit from Alice to Bob, okay, then, there's a bit of waste. And the best thing you can do involves, 2.6 bits on average. But if you know you're going to be solving this problem n times, like transmitting n copies, then you can like look at all the n tasks you have, somehow collate them together and get some savings. And that can also be true in this context of two-way communication complexity problems. But just like with entropy, like if you go to this refined measure that doesn't, that doesn't have to be an integer, that really measures like the real number amount of information, and they showed that it's like perfectly additive, like the amount of information you need to, that, Alice needs to learn about Bob's input plus Bob needs to learn about Alice's input to solve this problem f on like n independent instances is really n times the amount you need for a single instance. So that's cool. So in particular, since we have this intuitive fact that the communication cost is at least the information cost, tells you that like the communication cost for solving n independent instances of like function f on n pairs xi, yi, with error epsilon on each pair, is at least n times the information complexity. And so this could be a route potentially to proving lower bounds on randomized communication complexity, which in general can be quite tough. So let me save this fact up here. And I should say that like now I'm going to start telling you things at sort of a bit of a high level, and I will not be like 100% precise. And well, I think I will be precise. I think I won't tell you anything that's wrong, but like I'm going to hide some details. So remember last time, we talked about sort of the 3SAT of the communication complexity world, the disjointness problem. It was sort of this really hard problem. X and Y are strings, maybe representing subsets of the numbers 1 through n, and Alice and Bob have to tell if their subsets are disjoint or not. Or if you think of them as strings and you like stack them on top of each other, they want to tell if there's any coordinate where they both have a 1. They want the opposite to that answer. So really like, they do like a sort of a pairwise AND of their two strings, and then they want to see if there are any coordinates between 1 and n where that pairwise AND is a 1, and then because it's disjointness, you take the negation, but never mind. And we saw that, I told you it's a true but very difficult to prove theorem that even if Alice and Bob can be randomized, the communication complexity needed for this is linear in n. They can't do much better than just Alice sends her whole string to Bob. But a good way to prove it, to try to prove it, as I suggested last time, is through this information theory. And you see, it's kind of similar. So it's kind of like Alice and Bob have to solve n copies of like a teeny tiny problem of computing the AND between like a bit of Alice and a bit of Bob. It's not the same because like in this notation, really they have to compute n bits. They have to compute all the n answers, all the n ands. And in disjointness, you really only need to compute the or of the answers. You don't have to actually compute all the answers. But this is where I'm saying I'm going a little bit vague. I mean, this problem is pretty similar to like solving n independent instances, potentially, of a very simple problem, f equals the 1-bit AND function. And so if you want to use this, then you also need to have a probability distribution on inputs for disjointness. That's a product distribution. But it's like a product distribution across pairs. Okay, so you might ask yourself, okay, if the n bits, let me just put this up. So Alice is eventually going to get a string, and Bob is eventually going to get a string. And in this mindset, you're really interested in like, okay, we're going to have some probability distribution on their mutual first coordinates and some probability distribution on their mutual second coordinates. And we're going to use the same distribution for every pair of coordinates. But what distribution should we put on those pairs of coordinates to make it a challenge for Alice and Bob? So if we're trying to prove like a cool lower bound, we want to sort of think of a distribution that's going to make it hard as possible for Alice and Bob. And I'm going to ask you in a moment to think about that. So, well, that moment, I guess, is sort of now. So if you're trying to design a probability distribution on pairs of bits, mu, so you have to come up with 4 numbers, the probability of plugging in 0, 0, 0, 1, 1, 0, and 1, 1. And you want to make it tough on Alice and Bob for the point of view of them trying to decide if their sets are disjoint or if their strings have like a position where they have a 1 in common. What kind of choice for mu might you make? Notice, by the way, that this way of doing things gives strings for x and y for Alice and Bob that are not independent. The strings are not independent. The pairs of coordinates are independent. So one suggestion was that you could make mu be independent. So that would be like saying like, okay, I'm going to do a quarter, a quarter, a quarter, a quarter. And that actually corresponds to like x and y just being independent uniform strings. Thing is, at least intuitively, this does not make it too hard for Alice and Bob, because if Alice and Bob both get, completely random strings, then, 99% of the time, we're in fact like 1 minus 2 to the minus n of the time, the answer is going to be no, the strings are not disjoint, because like you have a quarter chance of having a column that's 1, 1. So like, probably you're going to have some column that's 1, 1. So this is not going to make it too hard on Alice and Bob. They can use the deterministic protocol that just always says no. And like they'll achieve an error that's like 2 to the minus, or 4 to the minus, maybe 3/4 to the n. Something like that, right? It'd be exponentially small. Somebody else suggested half, 0, 0, a half. Okay, that's interesting too. Here, let me get this one out. Let's think about it. Half, 0, 0, a half. Actually, this is not so good because basically, anytime you have, this is eventually the point I want to make. Maybe, yeah, somebody else suggested this too. Let's try the other thing. Let's try 0, half, 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 0. So what about this? Is this going to make it hard for Alice and Bob? Well, yeah, this one is not exactly going to be hard because actually, if Alice and Bob know that like this, then they actually know that they'll never be disjoint. So that's not so good. They can just always happily answer yes. Okay, we have another suggestion of 0, 1, 1, and 1 over n normalized. Yeah, I like it. 0. Let's think about this one. So the suggestion here is, let's put like 1 over n here. And that's actually a pretty good idea. And 1 and 1 here, or like maybe whatever, 1 minus 1 over 2n, but basically 1. So a good thing about that is, with this being 1 over n, basically, there's like going to be a constant chance that you'll have 1 or more 1, 1, so that the answer is sort of roughly equally likely to be 0 or 1, which is good at making it hard on Alice and Bob. This is reasonable. It actually doesn't hurt and may help to put some probability on here as well. But the main thing I want to get out of this discussion is, yeah, like the main thing is just to make sure you put like almost 0 probability on 1, 1, although not literally 0 probability. So the main answer I want to take away from this is, lots of mu's could be fine, but like mu of 1, 1 should be very close to 0. And here is another cool theorem. This one is hard, but true. And it says the following. It's kind of transforms this theorem into something that's like exclusively about like basically what happens if you do combining, not with you got to compute all the answers, but you got to compute the OR of the answers. They show that the communication complexity for disjointness when you use this n-fold copy of mu distribution is at least n times basically the information complexity of computing the and function under with 0 error under your distribution mu for any mu that has exactly 0 probability on 1, 1. Which is a bit funny, but this is the theorem that you can prove. And so, for example, you can take this distribution that's like 1/3, 1/3, 1/3, 0. And then it's funny, you just have to ask yourself, okay, like a question about like, 1-bit communication problem or an information theory problem. If Alice and Bob both get a bit, they have to have error 0, so they need a protocol that correctly determines 100% of their time if their bits are both true, if they satisfy and. And now the story is, 1/3 of the time they're getting 0, 0, 1/3 of the time they're getting 1, 0, 1/3 of the time they're getting 0, 1. And they're never actually getting 1, 1. But they still have to have a protocol that would be correct if they were getting 1, 1. What's the least information they can communicate in some sense? What's the least amount that Alice needs to learn about Bob's input plus Bob learning about Alice's input to decide the and function? This is actually, even though it's a problem about like 1 bit, it's actually surprisingly challenging. But with a lot of effort, you can figure out the answer. It turns out to be 1 over 3 ln 2, which is about 0.48. And once you know this theorem, you plug it in and you get that there exists some epsilon greater than 0. And this distribution, the n-fold product of this 1/3, 1/3, 1/3, 0 distribution, such that under this distribution, any protocol for solving disjointness with error epsilon needs at least 0.48 n bits of communication. And then by Yau's principle, you get that the randomized communication complexity of disjointness is at least 0.48 n. That's how you can prove it. It's actually 0.482 something. It's like slightly better to take a number that's like slightly different than 1/3, but close enough. Okay, so that's sort of story time about this. And let me just end with a little bit more story time, like one more slide or two more slides. So this is an old slide we saw with beautiful theorem number 1 about the exact additivity of information cost and how you can use that to like get a lower bound for communication bits of communication in terms of information complexity. And if you just take this inequality and divide it by n, we get this quantity. And we do that because we're thinking about amortization. You know, how much does it you need to communicate on average if you have to do n copies of some compute f task? So I'll put that all up here. And so this is true for every n. And so in particular, it's true in the limit as n goes to infinity. And I say that because this quantity here is really what you might define to be the amortized communication cost under distribution mu. Like, you know, if you're getting inputs from distribution mu, and you're trying to, Alice and Bob are trying to communicate to solve f, and they're going to get like a really large number of copies of this task, n independent copies. You can look how much bits they communicate, divide by n, and say like, okay, that's their amortized communication cost. We know that it's at least the information cost for, you know, just doing this one time. And so you might ask about the other direction. And that's beautiful theorem number 2 is proved sort of independently by Ma, Ishwar, and Gupta from the information theory community, and Braverman and Rao from the CS theory community. And they showed that they're equal. So it's exactly like with entropy capturing, like, you know, average case one-way communication. The average case, you know, two-way communication cost of solving a problem f when amortized out is exactly this information complexity quantity. And I'll just end by saying one word about the proof. You see what you have to do to prove the upper bound is you need to actually exhibit like a communication protocol, which really takes advantage of amortization, and takes like maybe a protocol that has like a lot of communication, but, you know, not so much information being conveyed, and compress it into like a short communication. And they do this. And so like their theorem kind of shows that any conversation that, even though it takes a long time, that conveys very little information, may be compressed to a short one, which is really, I mean, that's like that's deep. I mean, if you think about it, like that's a metaphor, yeah, for maybe these lectures or like just general conversing with people, like a lot of words sometimes, and you want to compress that down to just the right amount of information. Okay, so that's it. I shall see you again on Tuesday. I'll stop the recording now, but I'll stick around to answer questions.